Hello, my name is Tomislav Novak. I'm here at the University of Applied Sciences in Zagreb, and in this lecture we are going to talk about permanent storage of data using Labview environment. Let's say we have a measuring system that produces a lot of data that we want to analyze with some tool in the future. Sometimes the application needs to make sure that the data is available not only during the application execution but also in the future. So other applications, or maybe the same application, can access that same data. To accomplish that functionality, there are a few methods. For example, we can use a database, or we can use some kind of web service for storing data. But today, still, one of the basic ways to accomplish that is to use something that is called a file. So what is a file? A file is basically a group of data. When I say data, I mean a stream of ones and zeros that is stored in some kind of permanent storage. For example, a hard disk, a solid-state drive, or some kind of optical drive. When talking about files, we usually talk about different types of files based on how the data is stored in the file or how the data is accessed. So based on how data is stored in the file, we can say we have two main types. The first type is called a textual file, and the second type is called a binary file. This is somewhat confusing because the name binary files implies that it's stored in a binary numerical system, but we know that in any kind of storage we cannot save anything else but binary numbers. So both file types are basically storing binary digits, but the way they store that binary digits is different. So we'll learn what are the differences, what are the benefits, and what are the drawbacks of each of them. So we said we have a textual file and we have a binary file. So what's the difference? To understand what's the difference between those two types, we already said that whichever type of file we are talking about, we want to store, in the end we will store a stream of ones and zeros. So now we are going to talk how our application stores data and gets to the binary stream, and how the binary file is storing data so it gets to the binary stream. The easiest way to show this is to take some data sample, for example, a number, an integer number, like 123, and see what is the difference between storing that number into texture file and into binary file. So let's say this number is an unsigned integer that is 8 bits long, so it's basically 8-bit unsigned integer. So when we want to store that number into a text file, we basically take each digit of the number, transform it to a character, and we are storing each digit as a separate character into the file. So textual files are basically streams of characters. So when we use 123, we'll take digit 1 as a character, and we'll store that character into the file. We will then use number 2 as a character, and we'll store that character into the file. And we'll take number 3 as a character, and we'll store that in the file. So depending on what kind of coding we are using, so we have to transform the character into a binary form. So that means we have to get some kind of a number from this character and transform it into a binary system. So if, for example, we are using ASCII coding scheme, then that means, for example, AB ASCII coding scheme, that means that we are going to each character corresponds to one number. For example, 1 corresponds to number 49 in the ASCII table. Number 2 corresponds to number 50, and character 3 corresponds to number 51. So when we want to store character 1, we will store actually a number 49, and so on. That means for all the characters that there are. So 49, when transformed into 8-bit ASCII code, that means that we'll have 1, 2, 3, 4, 5, 6, 7, and 8 binary digits. So when 49 number transformed into a binary system, we will have 32 plus 16 and plus 1, all the other digits of 0. So when storing character 1 into text, I will actually store this string of bits. The same thing goes with all the other characters. So also number character 2 will be stored as a binary number 1, 2, 3, 4, 5, 6, 7, 8 as 0, 0, 1, 1, 0, 0, 1, 0, and also character 3 1, 2, 3, 4, 5, 6, 7, 8 will have 0, 0, 1, 1, 0, 0, 1, 1. So basically, when we store number 123 into text file, we will get this stream of data. On the other hand, when we store the same information into a binary file, we will store the number 123 as one whole number. That means that if when storing into a binary file, which data type corresponds to this number, that's how many bits it will be used in the binary file. That means that if this is a 8-bit unsigned integer number, that means that in binary file it will take up 8 bits of memory. So how this is converted into a binary system? It's very simple, because when you're storing a number into a binary file, we have to just convert the number 123 into a binary system and we will get what the binary file contains. 1, 2, 3, 4, 5, 6, 7, 8 bits. We said that this number is 8-bit unsigned integer, so we will have 8 bits. When we convert 123 into the binary system, we will have 0, 1, 1, 1, 1, 0, 1, 1. So we will see here the difference. When storing into text file, each digit is stored as a separate character, and when storing into the binary file, we just take the value of the number, we convert it to binary numeral system, and we store it as it is. Widely used textual files correspond to this. Some of these extensions, for example, the TXT file, a comma separated value file, some of the source code files, for example, .c or .java file, source code, and XML or HTML files are also types of textual files. On the other hand, the common binary files, for example, pictures are usually stored as a binary file, and movies also, that means video, executable files, archive files, and so on. So we see here that if we want to see what is the content of those type of files, we only need, for each of those types, we only need the notepad to see what the content, change the content. On the other hand, if we see these types of files, we cannot open all those files with the same application. So we have to have a separate application, usually have a separate application for viewing the images. We have a separate application for viewing videos, and so on. So that's the main difference between those two file types. So now we will see what is the difference between those two file types based on how the data is accessed into a file. So first, let's see what's with the textual file. When we store our data in the textual file, we are storing each digit as a separate character. For example, we want to store three integer numbers, like 157, number 2, number 50. That means that when we store it inside, we can store it like this. 157, then number 2, then number 50. So we store it like this. When we read the file, if we don't know, in the future when we want to read the file, we don't know what are the numbers that were stored in the first place, it is practically impossible to reconstruct the information that we wanted to store in the file. For example, when we are reading this file, we can read these characters as one whole number or as a separate number. For example, like a 15, 72, and again 15, or each character as a separate number. So when we store information into a textual file, we usually want to separate each record with a special character. Usually, for example, you want to store, so this is not a good way to store data into a textual file. So when we store, for example, these 2 to 3 numbers, we would like to store one number, for example, then use some kind of a special character that we'll use as a delimiter between each record. One of the usual ways is to use a blue line character to separate records. For example, in this example, we would store 157, then a new record will be stored in a separate line, so the second number will be stored in a separate line, so then the third number in the third line. So this way, when reading a file, we know that we can, when we read a stream of characters, and when we come to a new line character, that means that we came to an end of one record, and so on. That means for all the records in the file. For example, in the comma separated value file, each record is divided by a column character. So basically, in textual file, we have to separate our records with some kind of special characters. So when we want to read the content, we know when one record ends and when the other record starts. For example, in the copper separated value file, the records are divided by a column, and for example, in the XML file, the records are separated by special tags. On the other hand, if you want to store those 3 numbers into a binary file, and we said that how those numbers will be stored in the binary file depends on the data type that we use in our application for those numbers. So, for example, if we use the 32-bit integers for those data file types, that means that each of that record, each number will take up 32 bits in the memory. That means that if we store that number, of course, in 157, it will take up some amount of bits in the, it will take up 32 bits in our file, and when we store number 2, it will take up the exact same amount of bits in our file. So all those chunks of data are going to be of the same size. Let's say this is the same size in my picture. So when we store 3 numbers, we can see here that each number is 32 bits long. So we don't have to use some kind of special value to separate our records, because we know that each record is 32 bits long. That is characteristic of most of the binary files. So the difference between binary and textual file is that usually in textual file we have to separate our records, and in binary file we usually don't have to separate our records with some kind of special value, because we usually know where one record ends and another record starts. Also, because of that characteristic, for example, if we want to read a specific record in our file, for example, in textual file, if we want to read the 3rd record, we have to read the 1st and the 2nd record, so we can read the 3rd record. Why? Because we cannot jump in our file to the 3rd record, because we don't know how many characters the first 2 records consists of. So if when we want to get to this record here, we should jump for 1, 2, 3, 4, 5, 6 characters in our file to get to the third record. But we don't know. It could be that the first record was not 3 characters long, just 2 characters long, for example. In that case, the third record wouldn't be after 6 characters. It will be there after 5 characters in our file. So we cannot jump to the specific record. So it's we have to go through. If we want to read the 5th record, we have to read the first 4 records. Those kind of files are called sequential files. On the contrary, usually binary files, they are called direct files, because if, for example, if you want to read the 3rd record in the file, you know exactly how many bytes you have to jump into through your file to get to the 3rd record. So manipulation with data with binary files can be much faster than with textual files. So those are the main differences between 2 of the basic data file types. To conclude, we said that we have 2 basic file types based on how the data is stored in the file. We said that we have textual files, we have binary files. When storing data into the textual files, we said that we are storing characters, so we store a number. Each digit in a number will be stored as a separate character. When we store data into binary file, we said that we are storing basically data type. So we take a number, we convert it to binary numeral system, and we store it as in the number of bits that corresponds to data type we are using in our application. There are benefits of using both file types. We said that the benefit of using textual files is that because it uses usually a common coded scheme, we can open the file using a text editor, and we can change very easily the content of the file. So we said that we call textual files human readable files. On the other hand, when storing data into binary files, we usually you need to have a specific application to read the content. We cannot read the binary file. Usually we cannot read the binary file using a textual editor. Also, we said the records that we store inside textual files usually need to be separate with the special character. Textual files are usually something that's called sequential file. So that means that if we want to read the 3rd record, we have to read the first 2 records also. And on the other hand, binary files are usually direct files. That means that if we want to read the 3rd record, we can jump directly to that record and read, because all the records are the same size. We know how far we have to jump into the file to read that record. So those are the main differences between 2 main file types. So now we'll go into Labview environment and show you some examples of using each of these file types. So here we are in our Labview environment. Before we start, I just wanted to say that I'll be using something that is called a quick drop function. When you press Ctrl space, a quick drop window appears, and if you know a name of a block diagram element or a front panel element, you can just type in the name, and that way you can quickly find your element and place it on in your VI. So sometimes it's much faster than just navigating through the functions palette or through the controls palette. Applications that work with files need to know what is the location of a file. Information that tells us what is the location of a file is called a path. In Labview, paths can be retrieved using dialog boxes that are automatically started when programming uses some of the already built-in file manipulation VIs. So when the dialog is open, a user can choose a file in our file system, and that way our application can retrieve a path. When users of our application don't define what the file that the application uses, that in that case the program needs to create a path programmatically. Paths that are programmatically created are usually in some of the default locations in our file system, for example, a temporary folder or a documents folder, or they are relative to our application location. So Labview has already built in predefined constants that the programmer can use to create a path to a specific file. Those constants can be found in a functions palette, in a subpalette that's called file input output. A subpalette, and here we have a group that is called file constants. Here we have multiple constants that the programmer can use to create a path. So one of the constants that are commonly used is called the current VI's path. That is a path to the location where we saved our VI. It's very similar to something that's called application directory. Application directory is a path to where our application is stored. And here we have something that is called temporary directory. Temporary directory and default data directory. And the default directory, those are the paths to directories that are some of the predefined default locations for temporary files and data files and so on, and they can be changed in our Labview environment by clicking tools and options. And here we have a category that is called paths. Here we have all those paths to default locations, and we can change each one of them. They have some default value, and if we uncheck the use default values, we can change that path to something that we want. And also there are some of the built-in functions that we can use to create a path. So for example, in our functions palette, we can create, if we want in our application that we want to store a file or we want to open a file that is located in the same directory as our application, we can use, for example, our application directory here, and we can use a function that is called a build path function. It is also located here in the file input output subpalette. It's called build path function, so I will place it on our block diagram, and this function spelled using this build path function we can create a path that uses our application directory path, and we can append to that path for our application directory path, we can append a name of our file that we want to open or create, whatever we want to do in our application. So we can create constant here, and we can, for example, give a name to a file that we want to create or open or whatever we want to do. So for example, I will type in some mandatory name, so it's a file name, some generic name, and I will give it an extension, for example txt, and we'll see now that the output of this function will be I'll just create an indicator. We'll see that the output of this function will be a path that corresponds to this file that is located inside our application directory. So before I start this VI, I have to save my VI. So I will just click File, Save. Click File, Save, and here I see what is the path to my application directory. See here I have a directory, it's called File Manipulation Directory. Inside the directory I will save this VI. This VI will call paths VI. Okay, and when I click OK, now I will start my VI. I'll just expand this indicator so we can see what is the path to our file. So here we see that we created a path to our file that is called filename.txt, and it's located in the same directory as our application here. So that way programmers can create paths to specific locations that are more or less predefined. There are two main actions that applications need to do when manipulating with files. The first action is called opening a file, and the second action is called closing a file. So before we want to read a file or write to a file, we need to open it, and after we are finished, we need to close the file so the file can be accessed by another application or maybe the same application in the future. So the first action is called opening a file. In Labview we have a function that's called open, create, replace file. First we will see what are the inputs. The main input of this function is a path to a file. If we don't connect nothing to this input, then earlier mentioned a dialog will appear to user, and the user can pick a file from our file system, and its path will be used for opening or for opening our file. Or if we connect a path, for example, by creating a path with a build path function, that means that this function will open a file that is defined by this path we connected. The second input to this function is called operation. Operation will just create a constant. So create a constant. We see here operation it defines what we want to do with a file. So there are a few basic things that we can do with a file. We can open it. That means that the programmer is sure that the file already exists, and we just want to open it. Or if we know that the file doesn't exist, and if the programmer wants to create a file, then he'll choose create. There is also option that if the file exists, then this function will just open a file, and if file doesn't exist, this function will create a file defined by this path. Also, we can replace if the file already exists, and if it doesn't, we can create a file, and so on. Depending on what we want to do, we can choose each one of these options. The third input is called access option. This access option tells the function, open, create, replace function, what we want to do, what are we going to do with the file. That means, are we going to read the content, or we are going to write to a file, or we are going to do the both of them. So there are basically three options that we can do with the file. The third input is an error input to this function. So the outputs. The main output of this function is a reference to our file. So this reference is basically used by another functions that manipulate with files. Usually this output is used by write to file functions, for example, write to a textual file, write to a binary file, and read from binary and read from textual file. And also we have error output. When working with files, this error output, it is not good practice to ignore the error output. So handling errors is very important when working with files, because when opening a file, it is possible that file that we want to open doesn't exist anymore, so the error this function will generate an error, and so on. So basically, files is something that is controlled by our operating system, and our application needs to be prepared if something went wrong with some of the files. So that is why handling errors when working with files is very, very important. Okay, when we choose what we want to do with files, also we have an input that is called defines will the buffering be enabled or not. This input says that by default the buffering is enabled. That means that some kind of optimization is enabled. When writing to a file can require a lot of time, processing time. So optimization like buffering in our application is usually enabled, because it's much faster to buffer our data in our application, and when that buffer fills up, the whole buffer is written to the file at once. That means that way actual writing to a file is executed less frequently. Okay, when we define what we want to do with our file, usually we take our reference and connect it to some of the function that manipulate with file. That means the writing or reading to a file. We'll skip that for now and we jump right to the part that we want to close. Where we want to close the file. So for closing the file, we have a function that's called close file. Close file has two inputs. One input is a reference to the file that you want to close, and the second input is the error input. The error output of this file we connect to some kind of error handler. For now, I will just use some of the predefined error handlers in Labview. So I will just put a simple error handler here, and error output of this I will just connect to the simple error handler here. So now we have a basic structure. I will just get cleanup diagram. So we have a basic structure of working with files. That means we have here a part that opens a file on a specific path, or as I mentioned, we can disconnect this wire and the dialog will appear when VI is started, or we can define a path to a file here. And after that we have a part that it closes the file so it can be accessed by another. In the middle between those two, there goes our part of our block diagram that writes the data to our file or reads the data from our file. Okay, we will use this structure in all our future examples. In this example, we will show how to store data into a textual file. One of the common textual file formats is called a comma-separated value file. So, comma-separated value file is basically a file that stores records divided by a comma separator. So it can store data into multiple lines. So for example, this is a comma-separated value file, and we will create a VI that stores data in the file format that corresponds to something like this. So when using a file, we will use a template that is that we created in the previous example, that opens and closes a file. So we made a new VI and we'll just use the code that we created in the previous example, and we will just paste it here, and we will add the functionality of this example. So in this example we have to modify the parts of our opening part of our file. So the file that we are creating, that we are saving our data in, is going to be stored in our application directory. It will be called our measurement CSV file. So we will open a file, and or if it doesn't exist, we will create a file. So if the file, when we first time we run this application, it will create a file, and every other time we start the application, it will just open the already created file. So we'll write to the file. We will not disable buffering, so the default value for disable buffering will be it will stay the same. And in between those two main actions, between the opening of file and closing, we will input our VI that stores data, that generates data and stores data into our VI. So first thing we'll create a part of our application sub VI that generates our data. That data will simulate some kind of temperature measurement and time that the temperature measurement, the time when the temperature was generated. So between our part of our application that opens the file and our part of our application that closes the file, we will input the part where we store our data into textual file or separate value file. In our application, we will make a sub VI that generates our data, that simulates some kind of a measurement. For example, we'll generate data that simulates some kind of temperature measurement, and not only temperature but also time when the temperature was generated. So we will generate two values, temperature and time that the temperature was measured, and we will get some kind of array with that data, and we will take the data and store it into our separate value file. So first thing, we'll create a part of our application that stores, that simulates generation of some kind of measured values. So we will generate random numbers and between some kind of minimum and maximum value, and we will store the data into an array. So for generating those random numbers, we will use a sub-VI that I previously created. This sub-VI takes two inputs. It's a lower limit and upper limit, and on output it generates a number between lower and upper limit that we connected on its inputs. So we can just take a pick what the code looks like inside. So here we have a random number generated that generates number from 0 to 1. We multiply that by with the difference between those two minimum upper and lower limit of our numbers, and we will round up that to some kind of integer, and we'll add the lower limit. So on this one we get a number that is between the lower limit and upper limit. So with this sub-VI, we will put this sub-VI inside a for loop. So we will place a for loop here, and we will connect two numbers as an upper limit as also as a lower limit. So for example, we want to generate numbers between -80 and 80, so we'll just connect two constants to those two inputs, and on the output we will have a random number from between those two numbers. And we said that we want to store the value between those two numbers. We also want to store a time when the number was generated, so we'll use the function that's called get date time in seconds. So this, I picked the wrong one, get date time in seconds. So this function will gives us a time when this VI was executed. So we'll just combine those two values into one cluster and connect those clusters to the loop output. So to combine multiple values into one, we can use a bundle function. Bundle function takes as input, we will connect one value to one input and another, and the value that represents temperature to another, and we will just create a cluster as a representative cluster for this bundle function here. So I'll just connect that representative cluster here, and now we have a part that generates some kind of cluster that has two values inside, value that represents temperature and the value that represents the time when the temperature was taken. So if we just connect this cluster to the auto-indexing output of the loop, we will on the output terminal of this auto-indexing tunnel, we will get an array that has a number of elements that correspond to the number that we connected to this input here. So I'll just create control here, and we have control over our front panel. That course, this control, the user can define how many numbers the measure this sub-VI will generate. So number of data records that we will generate with this sub-VI. And also I said on the output we will have an indicator. So on the output we will have an array of values and the corresponding times. So now if everything is okay, I'll just I will circle this part of our diagram, I will clean up the diagram. Okay, and now to test this part of our VI, I will just enter some kind of a number here. For example, I don't know, 5 elements of 5 data records. I want to generate 5 data records, and I will expand this array indicator here, and I will just run the VI. We can see here that we generated 5 values, and each value inside is between those two limits that we created. And now we can use that data in our application to store it in our com-separate value file. I will create a sub-VI based on this part of our block diagram. So I'll just circle this part, and we can click edit and create sub-VI, and here we have a sub-VI that corresponds to our data generation part. So here we can also change the icon of this sub-VI, so we can so it's different from the other icons. So it doesn't matter, I will just cover the default icon appearance and place something that makes it different from the others. Press OK. I will save this sub-VI. Okay, save. Okay, and I will call it measurement simulator, like this. Okay, and now we have a sub-VI that generates some kind of data for our application. Now we'll use the data, as I mentioned earlier, and store it into our textual file. So for storing data into our textual file, that means that we have to use a function that writes to a textual file. The function that writes to a textual file is called write to textual file. It is located in the same palette that all the other file input-output functions are. So we just place it on block diagram. Here we have a functions palette. I will disconnect those two wires, and we see here that the write to text file function, one of the main inputs is the reference to a file that we opened earlier, and the second input is the text that we want to write into a file. The last input is the error input. So basically we want to connect the error output of our open function to our write to textual file input. So if this function generates an error, this function probably won't do anything, and we will connect that to the error input of our close file. So if the error occurs in any of these functions, the simple error handler will handle it, and usually just tells the user what happened with the file. So here, this function, it operates the way that it will execute only once. It will write whichever text string we connect to this input here. Okay, this reference we probably want to connect to the close file function. I'll just enable the label for here and enable label for here for this. So when our writing is done, we will close the same file that we opened. So this reference needs to be connected to all the functions that work with the same file. Here, in this part, we can just take all the elements from our array here, and each element that we take here, we will create a string that corresponds to comma separated value format and store it into a file. Because this array can have multiple values, we will take each of these here and we will in one iteration of a loop and create a string that we want to store into a textual file. So we'll use a for loop here. We will put the right textual file into a for loop. We will take this array and we will use auto indexing option again, but this time as an input tunnel, and that means that our for loop will execute the exact amount times that correspond to the number of array elements at the input of this tunnel. So basically this for loop will execute the number of that corresponds to the number of data records that we defined here. So what we have to do, we have to take each value inside of our array, and we will unbundle each cluster here, and we will create a comma separated value record here and connect that to our text input to write to measurement file. So that means that on this terminal we have in each iteration we have one cluster. We have to unbundle it, so we have unbundle function here. So we can just unbundle the values here, and we will create strings, one string from those two values, and store that into a file. To create a string from different file types, we can use a function that is called format int string function. So here we will place a format int string file. Format int string file. This format int string file can have as input multiple values that we want to transform into a string. So we will take the time value and we will take our temperature value here, and we will transform it into a string here, and that string we will store into our file. This format into string function we need to define the format of our data. So this format is basically taken from the formatting of strings in like it was in programming language, like in C programming language or C++. So we'll just create here a constant, and we will create a formatting string that formats our data into comma separated format. So I have already prepared this format in advance, so I will just paste it here and we'll go through it so you know what it means. We'll store our time as day, month, year format, and after that we will store comma, and after that we will store also an hour, minute and second value here, and after that we will have a comma, and then after that our temperature value will be stored in taking up three spaces. So now we have our application that generates some kind of measurement data. It means temperature corresponding time. We have a loop, that part of our application, that takes those records and stores each of those records into our file using this format here. Now we can just start our application. So here we can see what are the values that are generated. We can generate maybe multiple values here. We can start our application, and after that we will see if our we'll change the extension of our file from txt to CSV extension. It's not very important, but to be consistent with our example, we'll change that too. So now we can start our application to see if our file has been generated. So I will just press Ctrl R to start our application. So we can see that the application already executed. We'll go to the folder where our file is located. Here we have a file that's called measurement CSV file. We can open it with here the default application for opening CSV files is Excel, but I will open it with some other application, for example Notepad++. We stored our data into our file here, so we can see that here that the generated data in our application corresponds to data that was stored into our file, and this is basically the one of the easiest way to create an application that stores data into some kind of textual file. Of course, how the data is stored in the textual depends on the format of our textual file. So in this example, we will create an application that reads data from a textual file. In this example, we will use another file, very common file, textual file format. It's called an XML file format. An XML, for the purposes of this example, I created some kind of XML file, sample XML file that looks like this. So we see here that it stores some kind of measurement data. So XML file stores data that is placed between tags. So each tag has its own name. For example, here we have a tag that's called time, and between two time tags there is a time value here, and we have a tag that's called temperature. In between those two tags, the temperature tags, there is a temperature value stored. So, and we have a humidity here, also tagged all that where humidity value is stored between those two tags. So we have an open tag and a closed tag here. An open tag has a name between those two braces, and there is a closed tag also, closing tag that has this backslash character before the name of the tag. So when reading XML file in our application, we will try to create a VI that takes as an input the name of the tag that we want to read, and our application will read all the values that correspond to the name of the tag that we want to read. So for example, if our application takes as input temperature, a name, a string that consists temperature, our application will create a set of data that has all the values that are stored inside temperature tags. So for this data here, it will store 25.6, 22.6, and so on and so on. So basically our application will read data that correspond to the specific tag inside an XML document. So how to do that? First of all, we will use the, so I'll just copy this part here and I will paste it inside our example. It's called text reading. Okay, and I'll just paste it here. So again, we will place our code between those two parts of our main parts of our application. So first thing, we will what we are going to do with our file, we will read our file. So we will if we want to read our file, our program has to be sure that that file already exists. So we will open our file. We don't want to create a file. We want to just read the file, because if the file doesn't exist, then if it is created, it's probably empty. So it doesn't make sense to choose the open or create option here. So just open the file. We'll choose this option here. What we want to do with the file, we want to read the file, so we'll choose the read only option. Also we'll enable buffering here, as in previous example. Also, first we have to specify what is the name of our file that we want to read. Here we can, because our file is located, the file that I created is located in the same directory as our application, so I can use this name here and the application directory constant to specify the path to my file. So I can just paste the name of the file here, so this path corresponds to the file I want to open. Or I can just delete this part here, and this way the dialog will appear when I start my program, and the user can choose the file that we want to open. So just for that I will run my program here, and we see here that when my program starts, when this VI executes, I can choose, the dialog appears, and I can choose the file that I want to open. So I can just open this file, because this VI for now doesn't do anything good. It just opens the file and closes the file. There is nothing that can happen here. So okay, now first part of our application, our virtual instrument, is to read the content of the file. So first thing that we have to do, we have to use a function for reading our textual file. We can just open our function spelled. We have file input output, and we have a read text file function here. So as an input to our textual file, we, as already mentioned earlier, we need to have a reference to the file that we opened, and also we will connect an error cluster here, and we will also connect the error cluster to the close function, and we will, after we read all the data, we will close the file properly. And this is the way that we can read the data from our textual file. On this output we will get all the data that was read from the file. I will just create an indicator so we can see what is the content of that was read from our file. I'll just expand this so when I run the program we can see what is inside. Okay, I'll just clean up the diagram here. Okay, move this here. Okay, and now here, if we leave this function as it is, our function will read all the content of our file from the beginning to the end, and sometimes that is not what the program wants to do, because if the file is very large, that means that all the data that was read from the file will be stored in our memory of our program. So we can, with this input that is called count, we can limit the amount of data that we want to read from our file. So in this example we will not use that because our file is not that large, but in practice we can we probably want to limit our input data with this option. So in our application, we want to make sure that the user can enter the name of the tag whose values from the XML file he wants to read. So for that purpose, we have to place a string control on our front panel. So place a string control, we'll call it a tag name here, and we'll use that string to search through our file content string and try to retrieve the tag value. So first, before we start, I will just start this VI again and just to read the file content here. So what are we going to do? We are going, in our application, we are going to, when we read the file content, we are we'll try to find the opening tag position, and we will try to find the closing tag position in our file content string, and between those two positions we will try to retrieve the corresponding value. So first, what we have to do, we have to create a string that corresponds to the opening tag and that corresponds to the closing tag here, so we can search for that string inside our file content string. So to create an opening tag string, we can use a concatenate function, concatenate string function, that can take multiple input. So to create an opening tag string, we can connect the tag name to the second input, and on the first input we can connect opening braces character, and on the third input we can connect a closing braces character. So on the output of the concatenated string we will get the opening tag of this tag name. We will do the same for the closing tags. So I'll just copy and paste this here, and we can just add to the first input you can see that we can see here that the closing tags have a special backslash character here before the opening braces, after the opening braces, and so we can concatenate opening braces and backslash before the tag name. And now on these outputs we have opening and closing tags strings. So to search for those tags inside our file content string, we can use the search and split string. Search split string function. Search split string function takes as input two strings. First string is a string through which we want to search, and the second string is a string that we want to search for. And we have on the output we have a position of that string that we are searching for inside our string that we are searching through. So we are going to find the position of our opening tag, and we are going to find the position of our closing tag in our file content string. So we use two search split strings. So we'll search for the closing tag, and we will search for the opening tag in our file content string like this, and we'll get the position for each other. We can see here that, for example, if we take the time tag here, the start of the record is at the position that is corresponds to the beginning of the tag, opening tag, plus the length of that tag. So the record starts at the position that corresponds to the beginning of the tag plus the length of the tag. So to get that position here, we can add to the opening tag position, we can add the size of that opening tag. So we have string length function here, so we'll use the string length function to add it to the position of the opening tag, and now we have the position of our record here. So now we have a position of our record, for example, air temperature here, we have a position of our record, and we have a position of our closing tag. We'll use those two values here to retrieve the value between those two indexes. So to get that, we have a function that is called a string subset here. We'll take the string subset function, and the string subset function takes as input the string whose subset we want to take, and the two integer inputs. That the first input is the position of start of our subset, and the second input is the length of our subset that we want to take. So the first input is basically the start of our record, and the second input is the length of our record. So we'll just connect the value that corresponds to the beginning of our record, and the second input is the length of our record. Length of our record is basically the difference between the beginning of our closing tags and the beginning of our record. So we have to just subtract the beginning of our closing tags and the beginning of our record here. That's the length of our record. So that's the length of our record, and now here we'll create an indicator. So that indicator will show the value of the corresponding tag here. Of course, this VI here, it will only find the first occurrence of that value for the corresponding tag. So for example, we enter a tag for tag name a temperature, we'll only find the first value here. So we'll try to test this part of our VI. So for tag name we'll enter temperature, and so I will just clean up this part of our block diagram here and check one more time the VI. Okay, we have a error here, so we use the open parentheses on both parts of tag, so that's not correct. We have to use the closing parentheses for both tags here. Okay, so now it looks okay. We can try the program now, so I will just press Ctrl R here. We'll choose the file name here, and we can see here that this part of our VI works. Of course, this will only read the first occurrence of value, the first value that it finds that corresponds to that tag name. But if you want to make a VI that goes through all of the tags and retrieves all the values, we will probably have to put this side inside some kind of loop and iterate through the whole string here and retrieve all the values. So to finish this thing, we'll probably have to put some kind of loop, so use some kind of loop. So I will just connect, I will just put here so I'll just put here a while loop here, so just run this up here. So we have to connect stop terminal of our while loop. So what we are going to do, we are going to search through the whole string. When there is no more tags that correspond to the tag name, then we are finished. That means that if this output of our search split string gives us a value of -1, that means that in the input string there is no more strings that correspond to that tag name. So we just have to compare if the output of our search split string is equal to -1, that means that there is no more tags that correspond to our tag name. Of course, if we leave the program as it is, this way, that means that our VI will always search the whole string. But what we have to do here is we have to make sure that in each iteration we don't search the whole string, but when we find the first occurrence of our tag, Then we in the second iteration we have to search not through the whole string but just the remaining part of our file content string. That means that we'll probably have to use some kind of shift register here, and what we can do, we can use this match plus the rest of the string output or search split string here and place that inside our shift register, and so on and so on. I will skip that part here and leave that to the viewer to do it himself. So here we are, we added the remaining functionality to this sub VI. And the next step is we'll create a sub VI from this part of our block diagram, and we will use that sub VI to retrieve data from our file, that file content string, and we will display the data to the user. So here we created a sub VI from the part of our block diagram, and this sub VI takes as input a tag name, a file content string, and as an output it gives us an array of values that correspond to that tag name that takes as an input. So this indicator here should have all the values from the file that correspond to this tag name that we entered in the tag name control. So I'll just run this VI here so we can see if it works or not. I'll just press Ctrl run, we'll choose our XML file, and we'll see here that these values correspond to the tag name, the temperature. We can also check if it works for example, humidity. Here, I'll just press run here, choose our XML file, and here we can see that it works also for humidity. So in this example we are going to show what are the basic ways of storing data into a binary file. Earlier we said that when storing data into binary file we are basically storing data types. So similar to the previous examples, we are going to use a special function for store data in a binary file. It's called write to binary file. Write to binary file, we'll drop it on our block diagram, and similar to previous functions that we used for reading and writing to textual file, we have to connect the reference to our file, previously opened file. We have to connect error cluster. Also, we will delete those wires that connect directly to the close function. So, and we will also, binary files have to be closed after using, and we will connect the error clusters also. Now, if we look at the write to binary file function, we see here that we have two main inputs. The one input is called data input. We'll talk about it a little later. And the second input is byte order input. Some of the data types that we want to store into binary file, they consist of multiple bytes. So this input, with this input, we can define in which order those bytes are going to be stored. There, in theory, there are two main byte orders. The first is called little endian, and the second is called big endian. So let's get back to the data input. This data input is it's polymorphic. That means that it can receive different data types. For example, we can connect a simple numeric constant here. So I'll create a numeric constant, and we can, I'll just change the value inside, and we can connect that value, one numeric constant here, and we can see that this function write to binary file will store that value inside the file. How big the file will be, so that means how much memory will this data take in the binary file, depends on the data representation of this numeric constant. So we'll just see what is the data representation, default data representation for numeric constants. You can see here that it's a 32-bit signed integer. So if I start this VI here, The file that will store this data will be 32 bits long. That means its size will be 32 bits, that means 4 bytes. But before we start, we'll just have to set these values for opening binary file to the correct values. So first things, the file that we are going to save to, it will have an extension. Well, the extension is not very important, but we will say that the extension will be .bin. When we are, in this case, we are going to create a file if it doesn't exist, and if the file exists, we'll just replace the previous file. This is why, because we will run this VI multiple times, and each time we run it, we want to replace the previous generated file. And in this example, we will write a file, so we'll change this input to write only. When we set up all the values, we can run this VI. So I will press Ctrl R here. So after our VI executed, I will just go into a file, into the folder where my file is located. We know that our file is located into our player. We can right click on the file, and we can see here properties that this file is 4 bytes long. So if we change the representation of this data type, that means that representation, for example, to unsigned 8-bit integer, and if I run this VI again, so Ctrl R, so after my VI executes, I again go to my file and see here what is the size of the file now. So when I go and see the properties, I see that it's 1 byte long. So we can see here that which data type we are storing defines what is the size of our binary file. Also, except for this function, it's not only intended for storing one value at a time, it can also store multiple values. For example, we can connect an array of values to this input also. So I will create array constant here, and we'll put our numeric constant inside, and then we will connect our array to our data input. So I will expand this, and we will define multiple values here. So, for example, we'll activate, for example, 5 elements in our array. That means that this write to binary file function will store 5 unsigned 8-bit unsigned integers. That means it will store 5 bytes of data inside. The one interesting thing is that when storing arrays into a binary file, not only those values are stored, the first value that is stored inside the file is a 32-bit integer. 32-bit integer, the first value that is stored represents the number of elements in the array that was stored into a file. So if I run this VI here, our file will consist of 32-bit integer that represents the number of elements in our array, that means 4 bytes, plus the 5 numbers here that each consist of 1 byte. So our file should consist of 9 bytes in total for this when we store this array into a file. So I will run this VI, so I'm pressing Ctrl R. After my VI has executed, I will check the file size here. So I right click it, and we see properties here, and we can see here that my file consists of 9 bytes. If somebody is interested, you can use some kind of hex editor here, and you can check the content of the binary file. You can see, if you look into the file, you can see that the first 32 bits is stored in the file are represent the number of elements in the number of elements of array that we stored inside the file. Okay. Now, also, arrays are not the only data structures that can be stored in the file. We can also store clusters. So, for example, we can create a cluster on our front panel, for example. So I'll just create a cluster here, or we can create a cluster constant, it doesn't matter. Cluster constant here, so put inside the different data types. So we'll put inside a numeric constant that has a representation of, for example, a double representation, and then we'll put inside a numeric constant that has a representation of an unsigned integer, and again we will put inside a numeric constant, for example, another numeric constant that is a double with double precision. Numeric constant. So here, double precision numeric constant consists of 8 bytes, and this is 8-bit numeric constant. That means that we have 8 bytes plus 1 byte plus 8 bytes. That means 16 bytes in total for these two data types, and 17 bytes in total with this data type here. So if we connect this to the data input of this write to binary file function, and we run the VI, so I will press Ctrl R on my keyboard to run the VI, and now we check what is the file size of our file. So right click it, properties, we can see here that our file is 17 bytes long. Also, we can, if you have a hex editor, you can check the content of the binary file also. Okay, it's interesting also that you can connect, for example, an array of clusters also as an input to this function, and it will store all the data at once. So in the next example we are going to show, we are going to make an application that uses this knowledge. So in this example we are going to make an application that reads data from XML file. So we will use the VI that we created when in the example of reading a textual file, and we will store the data from the XML file to the binary file. So we will upgrade the previous example and add the functionality of storing data into a binary file. So we will create a new VI, and we will copy the copy the example that is reading from the XML file. So we'll just take the code and copy it, create a new VI, and I will paste the data, the code here. So now we can see here that we have a part that opens and reads the data from the XML file, and we have to add the part that reads the data, that writes the data to the binary file. So we have to open the second file here. So in this example our application will work with two files at the same time, not exactly the same time, but during the execution with both files. So I will just copy this part of opening a file here, and we will change the settings for each of those files. So the settings for opening and reading from the textual file remain the same, but the settings for opening our binary file will change. Also, we will need to close the file again here, and our error handler at the end will handle errors for both files in our VI. So we will merge errors for both files. Here we will use the merge errors function here. So we'll just connect the error clusters from both closed files, and we will connect it to the simple error handler here. And here we will have to change the settings for writing to our binary file. So here we will not open a file that already exists. We will create a file that already exists. So we'll change this to create, and with the binary file we'll write to binary file, so we'll change this setting to the write only settings. And also we will create a path programmatically for storing data into binary file. So we already did that in our previous example, so I will just copy this part here and use it in our current example. So here we have I have to find correct VI here. Okay, I found it, and we can use this part here for storing our data into binary files. So we will store our data into binary file that's called mybinary.bin, that is located in our application directory. We will create a new file when we start our VI, and we will write to a file. Okay, so we'll open a file here. Here we have a read from textual file. That is the part that we don't need here. Instead we have a write to binary file. So we'll just have write to binary file function here, as mentioned in our previous example, and we will use the reference also, and we will use the error cluster here. We'll connect the reference also to the close file function, and we will connect the error cluster also for closing this file. So what we have to do now here, as an output of our function that we created in our previous, one of the previous examples where we read from an XML file, we said that as an output here we have an array that has values for node, for a tag, for the node that is defined with the tag name here. So for example, if we enter on our front panel diagram a tag name, we will get an array that has values for all the nodes that correspond to this tag name. We said that we have a XML file that is something like that looks something like this. So we enter temperature tag name temperature, we will get all of the values that correspond to this tag here. So values from all the nodes that correspond to this tag name. So when we go back to our VI here, we what we want to do, we will use a tag name here, and we will get all the data for a specific tag name, convert it to an array, and we will change the data type of these array values here. So we have here an array of strings. We will convert this array of strings to array of numbers. So we will make an sub VI that converts an array of strings to array of numbers. So how to do that? So the first thing we're going to do, we're going to use a for loop here, and we will connect this array of strings to the auto-indexing tunnel of our for loop. That means that inside our loop, in each iteration we'll have one value, one string from our array of strings, and inside we have to convert that string to a number, because in our XML file we have numbers that are basically non-integer numbers. So we will convert it to a non-integer data type. For converting strings to numbers, we have some function that's called scan from string here. So we will just use this function. This function, I'll just turn on the label. So here we have a string. We can connect the input string on the input string terminal, and after that we can use this. It's very similar to the function we used when storing data to CSV file. Here we have to define the format of our how to convert a string to our data. So I need, just for purpose of this, I have to disable label so I can use this terminal here. I will just right click it and I will create constant here. And for example, if this string consists of non-integer numbers, that means that we have to use the corresponding specifier here. The corresponding specifier for non-integer numbers is the percentage sign followed by an F character. So that means that the input string will be formatted as a floating point number at the output. So when I connect this double output number output to the auto-indexing option of our loop, that means that each value from our input array will be converted to an element into an output array. So basically we'll have an array of strings will be converted to an array of numbers with this part here. If we want, we can test this here. So we can just right click it, create, and an indicator here. So we can see if the numbers correspond to the numbers stored in our XML file. So for tag name, we'll enter temperature like this, and also our binary file will be created. So before we run this VI, we have to connect something to this data input of our write to binary function. So we'll just connect some kind of numeric constant, so just to make it work. And we will have to change, because with the previous example, when we created a binary file, we created the binary file that's called like this. So we will just change the mode of operation to replace or create. So because this binary file already exists, we will just replace it with a new one, because we don't need the previous one already. And we will also move this indicator here next to our indicator, so each value to the corresponding place needs to be the same, except this will be the number, represented number, and this as text. So we have to enter a tag name here. So if we enter temperature here, that means that we'll read all the temperature value here. There will be shown in this indicator here as strings, and in this indicator here as a number. So I will just press Ctrl R on our VI. We have to choose the XML file here, and we can see here that our code works here. So we'll just convert it to our to a sub VI and use it to create our data for storing into a binary file. And when we converted our code into sub VI, we can use this sub VI to convert any data that was read from a file. So for example, we can just we can see here that we can connect the output of this converted number array directly to the input of this function that writes to binary file. And now we'll just try to clean up this part of our diagram. Okay, it's not much better, so I'll put it back here. So what are we going to do now is basically we are going to store the array of numbers that was converted from a string array to array of numbers and stored into our binary file. So now what we will get a binary file that consists of 5 double numbers. So I'll just run the VI. We can define the indicator, the XML file here, and we can go and see what is the what's the content of our binary file. That means what's the size of our binary file. Here we stored 1, 2, 3, 4, 5 double precision floating point numbers. That means 8 bytes of each record consists of 8 bytes. That means 5 times 8, that means 40 bytes of data, and 4 bytes for array size. So 44 bytes should be the size of this file here. So it is 44 bytes size here. So basically we stored our data from our XML file to our binary file. The next thing that we can do in this example is we can not only get the values for the temperature, we can also get the values from humidity. We can store that into an array of clusters and store and the temperature and the humidity into our binary file. So what we have to do, we have to get the humidity values also. So we will get another tag name here. So basically what I will do, I will create another control that will define the second value that we want to retrieve from the XML file, and we'll call it humidity here. And now that is the tag name too. So the second XML node function, we will with the second XML node function we will retrieve data for humidity, and we will also use the convert to number array function here. So we can transform this array of strings to array of numbers, and also we want to disconnect this array here, and we want to merge this array with this array into an array of clusters. So the first element of this array combines with the first element of this array here into one cluster. For that we have a function that's called index and bundle cluster array. So we'll just place it on our block diagram, index and bundle cluster array here. So we just expand it and we connect this array here with the second array here, and on the output we will get an array of clusters that consists of each of those values here. Before we start our VI here, we can just see what is the content of this array of clusters here. So I will just create an indicator here, and I will expand it on our front panel here, so we can see what is the content. Also, I have to connect something to this write to binary file just for this VI to work, to make sure that this VI works. So now I think everything is alright. We just run this VI, so I will press Ctrl R. We'll have to choose the XML file here, and we can see here that we have in this array of cluster we have the first element in the first cluster consists of the first element of the temperature and the first humidity here. So that means 25.6 and 44.99, and the second consists of the second temperature and second humidity here, and so on. So our part of converting our two arrays of values into one array of clusters work. So we can again improve our VI, so we can connect this array of clusters here to our data input of our write to binary file, and with this we basically accomplished what we intended with this example. I will just press the cleanup diagram here before I run our VI here. What we have here is basically we have an array of clusters. Each cluster consists of two double precision values. That means that in total we have 10 double precision values. That means 80 bytes. And we have, because it's array also, we have a 4-byte value that is stored into file, array size stored in it. So when I run this VI, I choose an XML file that I want to read, and now we'll go to our binary file and see what is the size of our file here. So we have 84 bytes that correspond to our predictions here. So in this example we are going to make an application that reads from a binary file. The binary file that we are going to use in this example is a file that is part of MNIST database. It is a database that is used as a data set for some of the machine learning applications that are connected with handwritten digit recognition. So in this example we are going to read a file that stores label informations for training data set. Data that is stored inside this file is structured this way. That means inside the file, inside this binary file, we have, first thing that we have a 4-byte integer. That means 32-bit integer that is something, this number represents something that's called a magic number. The second number in the file is also 32-bit integer, and it represents the number of items in the file. And after that there are number of items, amount of unsigned bytes, that that unsigned byte corresponds to one label of that data set. So what we will do in our application, we will read the second value here, that means the number of items, and after that we will read that number of items and use that number of items to read that amount of bytes, and we will show that to the user. So I stored the file here in the same directory where our application is. The name of the file is here, so I will just copy the name of the file, and we will use it in our application as a file name to create a path to this file. First I will have to copy the basic structure of our application. So I will create a new VI here, and I will paste our basic application structure for opening and closing the file. And after that, you see here we will build a path that corresponds to our file path. So I will copy the name of the file here. I'll just Control copy here and paste the name into our. Okay, and what we'll do with this file, we will open it and we will read the content of the file, and after we read the content of the file, we will show the content of the file to the user in some kind of indicator. So to go back to the file structure, we said the first thing that we are going to do in this example, we are going to read the second integer. We are going to read all the content of the file, but the number that we need is the number of items inside our file, and then we are going to use that number to read the rest of the numbers inside our file. So first thing we are going to read those first two numbers, that is some kind of a metadata of our file. So basically we are going to use a function as similar that in our previous examples, function that reads from a binary file, so it's called a read from binary file function here. So we will just connect the reference to the input, so it knows which file we want to read. So just connect the reference here. We will connect also an error cluster here, and we can see here that for now I will not connect the error cluster to the close function. So the first thing that we'll see here, that it takes also two inputs. The second input is the byte order, so we need to know what is the byte order of the data stored inside our file. The first input is the number of elements that we want to read. First, I said we are going to read the metadata, that means the first two 32-bit integers stored in the file. So what we are going to do, we are going to create a constant of a value 2, that means we are going to read two numbers here, and here we have something that's called a data type input. So each of those first two numbers is a 32-bit integer, so that means that we have to connect the 32-bit integer to our input, data type input. So we'll just create a numeric constant here, and we will change the representation that corresponds to 32-bit integer here. So this is can right click it, and we can see that the representation is 32-bit integer, so I can just connect it to the data type here. What we'll get on our output of here of this function, we'll see if we will create an indicator. We'll just create an indicator here. We'll see that the output is an array of numbers here, and for now we'll just read those two values here. I'll just connect the reference to the close function and the error cluster to the close function, and we'll see if we got if we created a good program that reads the first two values. So I'll just run the VI now. So I will press Ctrl R here. Our VI executed, and we can see here that inside our binary file we have 60,000 numbers stored after the first two integers. So what we have to do now, we have to use another read from a binary file function here that will read 60,000 unsigned byte numbers. That's because after our two numbers that we already read, we have to read the unsigned byte. We have to read 8-bit long numbers, and the number of those numbers is 60,000. So we have to use this second value here, so we can connect it to the count input of our second read from binary file function. So we will just, to upgrade our VI, we just have to disconnect this wire here. We have to connect the reference to the second read from binary file number, read from the function, and we'll connect it to the close function. Also we will disconnect the error cluster here, and we'll connect it to the close function. Now we will, as I said, we will use the second number here to connect it to the count number for the second function here. So to get a specific element from this array, since this is array, we can use an index array function. So we'll connect our array to the array input, and the index of our number of items is 1, so we just have to wire one constant to the index input here. So that means that from this array we'll get the element from the index 1, that's the 60,000 here. So the output of our function will connect to the count number of our second read from binary file. Okay, the second read from binary file will not read 32-bit integers as the first read from binary file function. The second read from binary file function will read 8-bit integers. That means we have to, the data type that we want to connect will not be in 32-bit integer. We will have to change the representation to the unsigned 8-bit integer. So the output of the second read from binary file will be an array of 60,000 elements, and each element will be unsigned 8-bit integer that represents a label in our data set. That represents one 8-bit number, unsigned 8-bit number. So we'll create an indicator here, create an indicator, and we'll just expand that indicator. Of course, we will not expand it to this, so we can see all the 60,000 values inside, but we can see the first few, so we can tell if it's working or not. So now we can run our application. So I will press Ctrl and R in our on my keyboard. When I press Ctrl and R on our keyboard, we can see that we read all the data from our binary file. We can see how many elements are in the array. We can use something called array size function. So we can connect the array size function to our array and create an indicator that can show us how many items are in our array. So this is the size of our second array here. So I will rerun my VI, so pressing Ctrl R now, and we can see here that our array has 60,000 elements. What is interesting in this example is that here we have two read from binary file functions, and first what we're going to do, we are going to clean up the diagram so it's more clear what we have here. So we have two read from binary file functions, and the first read from binary file function reads two 4-byte numbers, and after that the second read from binary file function reads the rest of the file. So how it is possible that first read from binary file function reads the first part of the file and the second read from binary file function reads the rest of the file, but they both read the same file? The reason for that is that when reading from a file, we have something that's called a pointer to a file position. The pointer, when we open a file, the pointer is usually located at the beginning of the file. So when we read some data from our file, our pointer moves through a file. For example, in our application, first thing what we do with our first function, read from binary file function, is that we read two numbers that are 32 bits long. That means that after our first read from binary file function executes, the pointer in our file will be located 8 bytes from the beginning of the file. So when we connect this reference to the second read from binary file function, the second read from binary file function will start reading from that position on. Also, at the beginning of our lecture, this lecture, we talked that binary files are sometimes can be characterized as direct files. Direct files, we said that are files that can access a specific record inside a file. So we can position our pointer at a specific position in our file and read specific record. So how to do that in Labview? In Labview we have a function that's called position set file position here, and we will use this function. I will just turn on the label. We'll use this function to set the position of a pointer in our file and read a specific record. We will do that before closing the file, but after we read all the records in our file. So to accomplish that, we'll just move these indicators a little higher here. Okay, this record's a little high here. We will disconnect these two wires here, clean up wires, and so we will use the reference from the last read from binary file function. That means that the pointer is at the end of the file at this precise moment, and what we're going to do, we're going to use these two inputs to the set file position function to position our pointer in a specific location. So there are those two inputs mean this. The first input is an offset. That's the number that corresponds to number of bytes from the position that is defined by the second input. So the first, we will create a constant here for the second input, and we can see here that the second input can be defined as three different values. The first value is the start value. That means that whichever number we connect as an offset, it will be relative to the start of the document. And the second is relative to the end of the document, and the third is relative to the current position of a pointer inside the document. So we will leave the position of the starting of the document. So for example, if we connect a constant number here, for example number 5, that means as a first input here, that means that when we on the pointer after our function set file position will be placed at 5 bytes from the start of our file. So after we change the pointer position in our file with set file position, we can again use the read from binary file function to read a specific record. So we connect the reference to the read from binary file function here, and we will read just one record in this case, and we will read one byte of because each record is 1 byte long. We will use the representation that we used for the second read from binary file. So the data type will be 1 byte long, that unsigned integer here. So at that specific position we will read one record. We will just connect the error clusters, and after that we will close our file here. But before we run our program, we want to make sure that we will read a specific record here. I will just change this indicator back to 0, so all the records are shown here. So let's go back to our file format. We said that in our file we have 4 bytes that represents our magic number from the beginning of the file. Then we have another 4 bytes that represent number of items, and after that our data begins. So each number in our data, each label is 1 byte long. So that means that if we position our pointer, for example, 8 bytes from the beginning of our file, we will read the first record in our file. So basically, if we connect constant 8 to the offset, and we that offset is relative to the start of the file, that means that after we read from binary file with that position, we will read the first record from our file. So that means that this indicator here that we will place as data output from the third read from binary file will read, I have to create an indicator, this indicator here will have to show the first record from our file. So I'll just run the file, so I'll press Ctrl R here. We can see here that we read the first record from our file. Also, if we for example, if we moved for, I don't know, 10 bytes from the start of the file, that means that we are positioned right before the third record. That means that if we run now our application, we will read the third record from our file. So I'll press Ctrl Run again, okay. And we can see here that we can position ourselves in any position in our file, and this is very useful if we have records that are of the same size, or if we know exactly what are the size of each record in our file, so we can read a specific record. So that's all for this example when reading a file. Hope it was helpful.